Hello everyone, welcome to sixth video in the series. In this video, we will discuss on thermomechanical analysis in Ansys Mechanical. The agenda for this video is as follows. We will start with the introduction, then discuss on flowcharts showing how thermomechanical simulation works, then discuss on different methods in Ansys Mechanical to handle thermomechanical analysis, and in the end, we will go through demos showing the modeling with some example for some of the discussed methods. For example, demo in which we will discuss static structure using thermal condition. Then we will go towards one-way coupling using native structural solver and APDL thermal solver. Then demo of coupled field static system, and finally we will also see a demo of coupled field transient system. So let's start with the introduction part. Whenever we say thermomechanical, this means that we are talking about two physics. One is thermal and other is a structure. Now from simulation point of view, there can be cases in which these two physics will be weakly coupled or strongly coupled. From weakly coupled, I mean that the structural simulation results are not going to significantly affect the thermal behavior. From strongly coupled, I mean that two physics are continuously talking to each other, means the deformation happens, it will change the thermal result. Now, as a designer, thermomechanical simulation helps us in answering these common questions like, will my component safe if subjected to some level of temperature? What is going to be the mechanical response at this temperature? Is a structural deformation further going to change the convection surface area or the location of the applied convection region? How the mechanical dissipation is going to affect the temperature and the local behavior? So if we look at these two images that I have put here, so I will put the paper links also in the description from where I have taken these images. So in the following images, two cases are shown. One for thermal stress and other is a case where mechanical dissipation will further change the temperature. For first case, the rise in temperature will cause thermal strain leading to mechanical stress in the model. For second case, the friction loss is converted to heat leading to rise in the temperature and further thermal strain and stress in the model. There are other common applications that are used, or mainly physics that are used for thermomechanical applications, like thermoplasticity, that is heat generated due to the plasticity, then thermoelastic damping, thermoviscoelasticity, in which mechanical dissipation are responsible for the rise in the temperature leading to further thermal strain and the stress in the model. Now let's talk on the workflow. I want to highlight that this workflow was created keeping in mind mechanical dissipation. If only thermal stress is concerned, then we can start from this portion. Like first we are going to perform the thermal analysis. We will get the actual temperature, that if the mechanical properties are something that is a function of temperature, then those things will get updated and then we will solve the structural simulation. But for just keep in mind, this is something that I created keeping in mind the mechanical dissipation effect on the full thermomechanical analysis. So in this workflow, the structural deformation will lead to mechanical dissipation, which will further change the temperature. So one example that I can, if I have to give one example, I can give you a disc brake example. So if we are trying to simulate the disc brake example, in which whenever the brake pad get engaged, due to the friction losses, there are going to be some local rise in the temperature. So we can set the mechanical boundary condition. Initial temperature is going to be like, if we can start with the reference room temperature. Deformation analysis, and whenever we are performing deformation analysis, it means that a disk is actually going to be at that state, in a rotating state. Now once that disk is going to engage, the friction loss will happen. That friction loss we will transfer to the thermal analysis with the thermal boundary condition like convection boundary condition or the radiation boundary condition, and we will specify the thermal properties. After that, because that whatever the frictional loss that we are converting is nothing but a heat source for the thermal analysis, so we will solve the thermal solution, we will get the actual temperature, mechanical properties will get updated, and again we will solve the deformation analysis. Now there are two ways to solve this problem. One using the strong coupling, in which the equilibrium is achieved by solver internally at each iteration. Another is one-way approach. So as we were discussing for the thermal stress analysis, so for that, what actually happens is that we solve the thermal analysis system and then directly pass the temperature result to the deformation to predict the thermal stresses in the system. But whenever the mechanical dissipation is happening, it is that we have to solve the problem as a multi-physics problem, because after each iteration, this whole loop is going to be carried out, and internally we need to find some type of equilibrium solution after each iteration. So again, in APDL there are two ways to handle even this two-way coupling type of problem. That is a strong way and the weak way. And I just want to highlight that whenever we are saying that splitting the thermal analysis and transferring the result, that is normally called as a one-way coupling. So there can be like one-way coupling, two-way coupling, and inside the two-way coupling, we can further classify based upon the naming convention given by the solver is strong and the weak coupling method. Now let's go to the next slide. So there are different approaches for solving any thermomechanical analysis in mechanical. So first is the very simplest one, in which, and it is something that is applicable for your like if you're solving using a static structure and with just a thermal condition. So most of the academic or the textbook problems you will be able to handle it, because there we actually assume a uniform temperature for the full body. So in that case, you can directly add one static structural system and apply a thermal condition. Another way is that one-way coupling using APDL solver. So as we discussed in the previous workflow, like if we want to use any one-way coupling, we can start with a thermal analysis, predict the temperature, and then pass it to the deformation analysis of the static structural system. So same thing has been done here. So here you can see one-way coupling using APDL thermal solver. So here APDL provides a way in which you can also solve the thermal equations, like the heat transfer equations using the steady state thermal analysis. So this will allow you to predict the steady state response. So once the steady state temperatures have been achieved, you can transfer those temperatures at the setup level. So that temperature will passed on as a like for example, imported temperature, and after that you can specify the boundary condition in a static structure to predict the mechanical stress in the system. Now the next approach is one-way coupling using external data. So this approach is helpful in the cases where you already have the temperature field available with you. Now that temperature field might be coming from the Fluent CFX or any other external tool that you might be working for this solving the thermal equations or heat transfer equation. So once that coordinate based temperature data is available, you can directly map those things in a static structure or the transient structure and then perform the this static structure or thermal structural simulation to predict the mechanical response. Now the another way is like if you are working with Ansys tools like Fluent or the CFX, then you can directly transfer the solution at the setup level. So only thing is that you need to work at a same workbench project. So you have to set up your Fluent model or the CFX level model in the same Fluent project, and then you can directly transfer those results. Then you don't require to use this external data procedure. Now the last, as we discussed, the two-way coupling approach. So in two-way coupling approach, you can use coupled field static or coupled field transient system. And here you can see the physics region has been defined. So for a single element in the model, we are solving both the physics like structure and the thermal physics. Now we will start going through some of the demos that I have already set up for you. Like for this case, and there are two cases, one for coupled field static and one for coupled field transient. So we will go through all those demos. So let's just start with our first demo. So in this case, what we are going to do is we have taken an example in which a stainless steel bar is initially at room temperature and heated till 200 degrees centigrade, and we are trying to find the stress developed in the bar. Note at one end there is a gap, so what will happen is that this bar is going to expand and hit this bottom block, and after that due to the contact that is going to get established between the bar and the block, so this cannot expand further and there are going to be some stresses inside the bar. So as this is a uniform temperature case, like because if we are going to apply a 200 degrees centigrade at this side, so what is going to happen is that uh, eventually this bar is going to uh, reach the temperature 200 degrees centigrade. So let's go to this example. This is my first example. So I have already set up and solved most of the cases. But what I will do is that I will show you all those boundary conditions and how you can apply those boundary conditions inside the GUI. But I'm not going to resolve the model. So let me open this model. First, change the viewport to a single viewport. So this is the model. So CAD geometry I have already created in the space claim because it was simple. And as this bar has some gap here, so you can see if I zoom in and put a view of this one, so you can see there is some gap. So once that body is going to get subjected to 200 degrees centigrade, then the contact is going to get after some time the contact will get established, and then the stresses will build up. Now the next thing is that because this is some type of nonlinear contact, so we have to define some contact. So you can define the contact under the connection. So if you right click, insert manual contact region, and here it's a frictional one. All the settings are left as a default one, and I have provided a frictional coefficient of 0.25. Next is that for time being I'm going with a default mesh setting, and after that, as this bar is going to be fixed at one end, so you can add this fixed boundary condition. So if you right click, insert, and then you will find the fixed support boundary condition here, and then you have to select this face, and once you select the face and hit on apply button, then fixed boundary condition will get applied. Second is that this block is the bottom block is also fixed at one side, so I had applied a fixed boundary condition at this position. Next is that we have to add one thermal condition. So if you insert, you will find the thermal condition. Now you can apply the thermal condition to any of these bodies. So as I want only these bodies to expand, so I can apply the boundary condition, and then we can ramp the values from 22 to 200 degrees centigrade as a steady state analysis system, so there will not be any transient effect. Now if I'm going to quickly solve it, I think somehow the results got overwritten, so I have to resolve it. Now if I'm going to look at the equivalent stress, so first thing you will notice that the stresses are very high. So the reason is that as we are applying some fixed constraint on this face, so this fixed constraint will not allow any of the nodes to expand, but due to the thermal expansion, this face will try to at least expand in the tangential direction. So we are forcing it to not expand in that direction. So that's why there is some singularity that is happening here. But in this case, we can ignore this one because our area of interest to see how much stress is getting developed in this bar, and we can also see it is very localized. So there are ways to remove this fictitious singularity. So I will put some blog or links in the description that actually discuss this thing in detail, how you can avoid this stress singularity in this specific region. So now if we look at this values, so I can see that in this region 133.12 megapascal is happening, and also I can confirm that these bodies have been come in contact or not by adding a contact tool. So if you go here, contact tool you can add, and under the contact tool I can look at the status. So I can see the status is sticking. It means that those two bodies, for those two bodies, the contacts have been already established, and we can also look at the pressure that is building in this region. So this contour pool plot looks a little bit patchy, but if you are going to refine the mesh, then this patchiness will go away. So this is one way. Now at this point, suppose, because usually for thermal condition cases, whenever we are going to subject any material to 200 degrees centigrade, the material properties are something that is temperature dependent. Because at 200 degrees centigrade, your young modulus is not going to be same as 22 degrees centigrade. So for defining the engineering material properties as a function of temperature, if you go and click on this isotropic elasticity, you will see that you will get an option. So at this point you can enter, like suppose here I can enter, this is my value for 22. I'm just taking some random values. So I'm assuming that at 200 degrees centigrade my material properties change to something 2e to the power 10. You can see this is linearly getting interpolated between 200 degrees centigrade and the 22 degrees centigrade that we applied. Let me, it's showing some question mark. Okay, so we have to enter Poisson's. So I'm keeping Poisson's ratio temperature independent. Now if I go here and if I refresh the materials, go to this structural steel, isotropic elasticity. I can see the values that are getting imported from the engineering data are actually temperature dependent. So this way you can include the temperature dependence also inside the model. Now the next is that suppose on the same problem statement, what we assume is that previously we were assuming that the bottom block is something that is also kept as a 200 degrees centigrade. But suppose in this case, if we assume that the bottom block is something at as a 100 degrees centigrade and there is no gap. So just you can ignore this gap. So for this problem, we will assume that there is no gap. Only thing is that the top block is kept as a 200 degrees centigrade and bottom is 100. What it actually means is that if there is a variation, like if on both the sides we are keeping different temperature, it means that there is going to be some temperature gradient. So this can be solved only through some thermal solvers. So Workbench APDL also offers a thermal solver which will allow you to solve conduction, convection and the radiation part. So that can be added either using the steady state thermal or you can use a transient thermal in case if you want to also see how the temperature is rising with time. Now if I'm going to open this one, so this setup looks something like this. So here under the steady state thermal, you will get access to all those temperature boundary conditions. So for this case, I'm applying a temperature of 200 degrees centigrade on one side and on another side, I'm applying 100 degrees centigrade. Now one thing is that as these two bodies are in contact with each other, so we have to define some type of bonded contacts. So here you can see whenever we are defining a bonded contact, by default, the thermal conductance will get computed internally by the solver, and that is usually very high to ensure a perfect conductance across these two bodies. Now if we look at this one, so we can see this temperature is varying along from 200 to 100. Just to get a better clarity, what we can do is that we can plot the temperature for this edge and I can convert it to path, and if now I'm going to evaluate all results, I can see this temperature is going from 100.0. So this is some numerical fluctuation we can ignore to 200 degrees centigrade. Okay. Now the next thing is that if you are going to transfer the result, so what you can do is that you can add one static structural system and then connect this solution to the setup level. So one way is like you can do it in this fashion. Another thing is that you can, if you are working in the GUI, yeah. So you can go to this analysis system here, and from here you can add some static structure. So once you add the static structure, and then again go to the workbench base, you can transfer this result. And now if I'm going to open it, you can see one imported load is coming. So this imported load will allow us to map the temperature for all these bodies. So this will allow even to means you can control that on which body you want to map the results. So suppose if two bodies are not of our area of interest, we don't want to see any we know that the thermal expansion or thermal strain that is going to get developed in this body is not so significant compared to the bottom middle one, then we can ignore this body also. Now the next is that you can add the boundary condition as on both sides, fixed boundary condition, and then you can solve the model. So this is like one-way coupling in which we are first solving the thermal problem. We are getting the temperature, then whatever the temperature that got generated in the model, we are mapping those temperature to the static structure and then predicting the thermal stresses in the model. Now the next is your coupled field system. So for coupled field system, the problem I have expanded little bit. So for that, what we are going to assume is that on one side there is a 200 degrees centigrade, another side there is 100 degrees centigrade. Also, we are trying to move the block in some specific like by 0.2 meter. So let me show you that model also. So So this is the model. So here you can see what I'm trying to do is that I have applied 200 degrees centigrade on this side. On this side, I have applied 100 degrees centigrade, and I'm also trying to displace this block by 0.2 meter. So it's like this block is also moving in this y direction. So this is like a coupled field problem. So if something is moving and also the temperature along with the temperature variation, if you want to solve the problem, then we need to use the coupled field system. So this is just one of the example. Now me delete this one just to show you. Okay, so if I activate the vector view, you can see this block is actually moving in this direction. And after some point, the contact will get established. And then even after, there will be two things. One is that as we are pressing this block, so the contact pressure will build up, and that will also cause some mechanical stress. On top of that, there is going to be the thermal stress that will get generated due to the thermal strain. So you can also see the temperature. So temperature is getting captured like 200 to 100 as we have established using the temperature boundary condition. And also we can see the equivalent stress. Again, there are some singularities in this region, but you can ignore. And we can see this 302, 297, 297, 297. So for this case also, if you want to define some type like material properties as a function of temperature, then you can use the engineering data as discussed previously. So if you go here, Young modulus, again you can enter those things as a temperature dependent properties. Now the next is that coupled field transient. So this is the same problem, but in this case, what I'm trying to also find is that how much time this, like suppose if I'm subjecting this block to 200 degrees centigrade, how much time it will take for that 200 degrees centigrade to build inside this model. So as we see this thing like temperature variation, you can see over a time, it is actually building up. So let me 200 degrees centigrade, and to get a better idea, let us plot for this body, and here you can see this is actually, if I'm going to, I have not created all the results, but you can see the temperature is building over a span of time. So this actually helps us, like suppose if you have some problem in which you are inducing some type of heat and you want to know after how much time that body will get heated to some specific temperature. So in those cases, you can use this approach. We will take some other examples in our upcoming videos, but for a timing, keep in mind that if any evolution of parameter or the temperature, if you want to track with time, then you can use either transient thermal. So in that case, only thing is that you will not be able to solve everything in a coupled fashion, but you will get the temperature variation as a function of time. Here you can see the same thing has been done. And also, if suppose if we look at the contact pressure, you can see this how the contact pressure is building over a span of time. So initially only that in first load step only that, because we had applied something like if you look at this one, you can see the maximum is around 75.454. So this actually builds up because we are trying to displace this body in this direction. And after that, whatever the contact pressure change is happening, it is happening because again due to the thermal stress development, this body is again trying to push this body in y direction. So that is the reason we are seeing some variation in this contact pressure. So even the contact pressure looks high, so because this is something that will not be feasible and even the material will not be able to handle. So for handling this problem in a proper way, you can define some type of further plasticity in the model. So that plasticity will allow you to further capture the redistribution of the stress in the localized region. So thank you. That's all I wanted to cover for this video, and see you in next video. Thank you. And if you like the video and like our series, please don't forget to like and subscribe the channel, and you can also share this video with your friend and colleagues. Thank you.